So Yang, I started sharing my screen again. You can see my mouse move.
Yes, I can see your screen clearly.
Very good. And my mouse. Good.
Good.
Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present and future is the mission of Eco-Environment and Health. Eco-Environment and Health is a journal initiated by prestigious scientists with a strong editorial board including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design and broadcasting. The experts will accompany you like a harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Okay, that's the brief introduction of the journal EEH. We still have 3 minutes before our presentation. Maybe Hans-Peter, will you submit a review manuscript to EEH in the future?
Well, I have to now after seeing that video. It's quite impressive.
Yes. This is a newly issued journal. I will make a brief introduction later. And the instant impact factor has been, I think, is higher than 7 now. In the next year, maybe the impact factor will exceed 15, I think.
Okay, wow, that's very good, very ambitious.
Maybe you can write some manuscript revealing commentary to this journal, especially the microplastics. I think is really hot topic now. And of course, the PMTs you mentioned in this presentation is also very hot topic, not only in Europe, but also in China, I think.
That's very good to know. Yeah, no, I definitely should. Because right now there's a big also focus to try to make PMT more international, because it's been mainly a European focus, but we're trying to get other countries to think about this issue as well.
Okay. So the time is gone. So let's start with this talk at EEH. Good morning, Hans-Peter. Good morning, everyone, and good afternoon for the audience in China. Today is my great honor to host this webinar. As you can see from the video, EEH is a new worldwide journal which is issued by Nanjing Institute of Environmental Science, Ministry of Ecology and Environment of China, and Nanjing University. In talk at EEH, we invite world-famous experts to give the presentations of the hot topics. Today, we sincerely invite Professor Hans-Peter Arp from Norwegian University of Science and Technology to give us a talk about PMT substances. So firstly, on behalf of all the audience, I will give a welcome applause to Hans-Peter. Although the applause sounds not big enough, but from only myself, but it's really a warm. Firstly, I will make a brief introduction of Professor Hans-Peter to everyone. Professor Hans-Peter Arp is an expert advisor at the Norwegian Geotechnical Institute and a professor in the Department of Chemistry at the Norwegian University of Science and Technology. His research is focused on both fundamental and applied aspects related to the fate, behavior, and transport of chemicals and plastics in the environment. His recent project study fate of chemicals during diverse waste handling process within the context of best management practice for hazardous chemicals within a circular economy. Many of his current research focuses towards the safe and sustainable recycling of sludge, plastics, and e-waste. Since 2016, Professor Arp has conducted 2 large research projects for the German Environmental Agency to assist in the development and implementation of criteria and guidance to identify substances that are persistent, mobile, and toxic, namely PMT, or very persistent and very mobile, namely VPVM. Recently, a version of this criteria was adopted by the European Commission. This work is now being followed by 0PM, which Professor Arp is a coordinator of. Today, Hans-Peter will give us a presentation titled Confronting the Threat of Persistent, Mobile, and Toxic Substances to Protect Water Resources. Really an interesting and hot topic nowadays. So according to the demand of the editors of the office, if the audience have any questions or comments, you can raise your hand by the bottom and Zoom. Then your mic will be open. During the presentation, your mic and your camera is closed. Or you can type your questions in the chat box. I will read the comments or questions one by one after Hans-Peter's presentation. Okay, now, Hans-Peter, you can share your screen and begin your presentation, please.
Yes, well, thank you, Professor Yang Song, for that very nice introduction. I'm sharing the screen now, and I hope you see it. Great. And yes, so I'm looking forward to giving this this presentation on persistent and mobile and toxic substances that Professor Yang Song just introduced. Now, the presentation is going to be in 4 sections. So first, I'll talk about the increasing contamination of these PMT substances. Then I will go over the European regulatory developments that Professor Yang Song mentioned in the introduction. I then have a section on how to identify new PMT substances. And then I'll end with what I think is the most important part, is about zero pollution and how we can avoid pollution of these substances. So, so to start off, this is the part 1 on the increasing contamination. Definitely, I've seen in the media here in Europe, there's been more attention by the general public about these types of contamination. These are different clippings from European news articles where people are concerned about more chemicals showing up in their tap water and in their water, and also on their soil, because often the cause of these contaminants in the water are in the soil, and it goes into the groundwater and enters the soil. And this is becoming also an issue in America, where they're coming up with stricter regulations, and also in China. So I've been collaborating with Professor Biao-Jin in Guangzhou about PMT substances, and it's getting some attention there as well. Now, I'll just give you another example of what this can look like. So I'll explain this graph. This is from a water source, a drinking water source in the country of the Netherlands. And they're looking for new chemicals that are in their water supply. And the purple dots are the new chemicals that they are finding in their water supply. So it went from 4 to 626 in the past 22 years. And these are the ones that they consider are actually harmful to the people drinking the water. So they have to take special note of. And this increased from 4 to 36 chemicals. And all these chemicals they consider persistent and mobile. And this has caused the cost of the drinking water production to the people in the Netherlands to increase. So it's a big cost issue for them, and the taxpayer who might have to pay for the drinking water quality. So the question is, how did these chemicals get in the drinking water? And I have a picture of me giving water to my son. So obviously, chemicals are made somewhere in a factory, and they're made for diverse uses and products or processes. But it can be at some point in the chemical life cycle, maybe from the beginning where it's being made in the factory or where it's being used, that at some point it might enter the environment through different ways. So these are the environmental emissions. But once you have these environmental emissions, they might be transported into a water production plant where they make drinking water. And if it's even able to go through this drinking water plant, it will end up in my son's water bottle, which is what we want to avoid. What kind of chemicals, though, can do this and survive this journey? They have to be persistent, meaning that they don't degrade during this time. They have to stay as this chemical structure, and they're mobile. They actually have to be moved in the environment. So that's P and M in PMT, and the T is toxic. So if any of these chemicals are toxic, then this is a serious concern. This is an example. One of the most famous, well-known PMTs are PFAS in water. PFAS is poly or perfluorinated alkyl substances. So these are heavily fluorinated molecules. And this was a study in global tap water from 2016, 2018. And they included even samples from China, from Beijing, Canton, Dongguan. And basically, they did find PFAS in tap water all over the globe. And it used to be previously one of the strictest drinking water limits for PFAS in people's tap water was from Denmark. And they had a limit of 0.02 micrograms per liter or 2 nanograms per liter of these 4 PFAS substances. And so already then there was several cities that were exceeding this limit in their drinking water, like Montreal or Quebec or Toronto, Chicago, Ouagadougou, Tokyo, Paris. China not, but then what happened recently, they're finding that PFAS are a lot more toxic than they thought. And so the Americans, they actually reacted to the most recent toxicological data, which was related to children with high exposure to, or people, animals with high exposure to PFAS having less good positive effect from vaccines, like the tetanus vaccine. They lowered their drinking water limits to something extremely low. This is in the picogram per liter level. And this is actually a challenging for many labs to measure. This is such a low concentration of these 2 chemicals. And so when you look at this as your safe level of drinking water, it turns out the entire globe could have contaminated drinking water. And so this is maybe exceeding a planetary boundary. And I'll give you another example that I find is very illustrative. It's one of my, an example I like to focus on. It's one of the smallest PFAS you can find. It's called trifluoroacetic acid, or TFA for short. It has this structure. It's just carbon with 3 fluorines and then carboxylic acid. So it's basically fluorinated vinegar, pretty much. But it was quite shocking when they did a survey in Denmark. It was in 2021, where they looked at groundwater throughout the country, and they found this chemical in all the groundwater wells in the entire country, up to concentrations of 2.4 micrograms per liter. But this is well known. We're seeing more measurements of this chemical in the environment, of TFA. In Germany, they had it in tap water, in their drinking water, up to 20 micrograms per liter, and in river water up to 120 micrograms per liter. And there's even it was a Chinese survey where they looked in blood samples. And they found in 97% of the blood samples, there was TFA detected with a median concentration of 8.5 micrograms per liter. So this is a new substance that's in everybody's blood. Where does this come from? They point to 2 main sources. One is in plant protection products. So these are used on farms and quite high quantities, including in Denmark. which can break down in the soil by microbial processes to make TFA, and then they can enter the groundwater where they eventually meet the drinking water. Another major source is refrigerants. So if you know about the Montreal Protocol, there used to be chemicals called chlorofluorocarbons or freons used in refrigeration pumps. This was now changed to other molecules like hydrofluorinated compounds and hydrofluorinated olefins. And these are produced in high quantities. And these also break down in the atmosphere to TFA. So these are the two of the major sources. And there's also other sources of TFA. But one thing they find now in the environment, so this is a study from polar ice cores. So in Greenland and in northern Canada, where they looked at the ice cores and they can see that the concentration of TFA landing in the ice is increasing with time. And they can even pinpoint the date to when this increasing trend occurred with the Montreal Protocol when they switched from chlorofluorocarbons to these precursors of TFA. Now, what I find a little bit concerning about this in particular is that it's accumulating in the environment. So we know that the concentrations are getting higher and higher. Now, some people might say this is not a big deal. It's not a big deal that we have TFA in our blood. It's not a big deal that we have it in the water because it's not toxic. But I say we can't assume we always know when something is toxic or not. The lowest observable effect concentration so far for TFA is this microalgae, and it has a concentration of 120 micrograms per liters. So it's true that the environmental concentrations are just below this, but maybe we find something else that is more sensitive to TFA, or maybe we find that humans are more sensitive to TFA. And the problem is once we hit a limit, we won't be able to do anything about it because it's already distributed ubiquitously in the environment and it doesn't break down. So basically the TFA level that we have in our ocean now, our children will have in their ocean and our grandchildren will have in their ocean. And maybe the levels of TFA when we have in blood will be there for several generations. So we just better hope that it never increases to a concentration that causes problems. But because of this, because of the accumulating nature of it, I consider this a planetary boundary threat because it is a chemical that we want to stop accumulating. But it's not just PFAS. So far, I gave you examples of PFAS, but non-perfluorinated examples of PMT substances are melamine, which has been in drinking water up to 2 micrograms per liter. It's toxic to kidneys, especially in combination with a structurally related compound called cyanuric acid. And we've seen in many drinking water samples here in Germany that you can have melamine and cyanuric acid in the same drinking water sample up to 0.12 micrograms per liter. 1,4-dioxane is another chemical that's under increasing scrutiny. It's a PMT substance and it's been seen up to 0.8 micrograms per liter and it's carcinogenic, 1B. And benzotriazole is another one. This is a chemical used in a lot of detergents to prevent the metal from rusting inside the machines. And this has been observed in drinking water up to 0.2 micrograms per liter and exceeding national country limits. One thing that I have to emphasize is a lot of these PMT substances are also not easy to remove when you're making drinking water. So there's several technologies out there to clean drinking water, but they all have limitations. So activated carbon is not good for the very small molecules. Anion exchange resins that are used are not good for cations, and cation exchange resins are not good for anions. And so you can also use more expensive techniques, which are extremely expensive, called reverse osmosis and nanofiltration, but they'll even let some very small molecules go through. For instance, melamine will go through reverse osmosis. And then you can use advanced oxidation processes to try to break down these molecules, but you never know what they break down into. And this is some results that will be published soon, but when we did a survey of drinking water facilities in Germany and also some of our own testing, we took a list of 150 of these PMT VPVM substances, and we found for half this list, ozonolysis and activated carbon did not work at getting rid of them in drinking water. And these are the two most common advanced techniques in Germany. And so it's expensive. So like I always emphasize that this issue is not just a health issue, but it's also it's a water quality issue and drinking water quality issue. For instance, if you wanted to use reverse osmosis on all the drinking water in the world or in Europe, it will cost you something like €1 per cubic meter. I should have translated this to other currencies, but it's €1 per cubic meter, and it costs 1 kilowatt hour of electricity per meters cubed. And so therefore in Europe, just if you're treating wastewater, this would be 200 billion cubic meters a year, or if you're just drinking water, this is 38 billion cubic meters per year. And so we're talking about costs, and I mean, this is an extreme estimate, but we're talking about extreme costs, about 238 billion euros a year for Europe, and a lot of emissions of CO2 to get this energy going. And this makes everything that we might want to do when we have limited water supply, like recycle wastewater, it makes it more expensive. So the fewer PMT chemicals we have in our water, the cheaper it is to recycle. So that was part one of my talk, which was to make you interested in the topic. Now I'll talk about the recent regulations in Europe that they have done to do some action on these chemicals. And a key document that I was involved in and involved with the German Environmental Agency, which kind of set the framework more or less for these regulations, is these two documents that were published in 2019. This was written by my regulatory colleagues in the German Environmental Agency, Michael Neumann and Ivo Schliebner, where they defined what is a PMT substance and a VPVM substance, and the criteria, the hazard criteria to use in chemical regulations. And I, with my colleague Sarah Hale, worked on the scientific background and information as the basis of this criteria. And it was developed through several consultations and workshops with diverse stakeholders. But one thing that was important for us to argue in this was that there was a similar regulation for chemicals called persistent bioaccumulative and toxic, as opposed to persistent mobile and toxic, and very persistent, very bioaccumulative. And we thought that the risk of these chemicals, which are already regulated in Europe, should also be applied to the PMT chemicals. And the reason why is because both chemicals can accumulate in the environment. PBT chemicals accumulate in the food chain. They accumulate in the lipids of humans and in animals, and then they can accumulate in the food chain through lipids. Whereas PMT chemicals can accumulate in water resources, like the trifluoroacetic acid. Your groundwater will just get more and more concentrated. And then you can have, that would be the irreversible exposure. And because these chemicals are around for some time, because the PBT chemicals are in the body for a long time, and because the PMT chemicals are in the drinking water for a long time, if the health effects would be irreversible because we can't remove them. The drinking water facilities can't remove them. So we say it's irreversible exposure and irreversible health effects. And then responding to this, the most recent thing was in December of last year, in 2022, the European Commission developed the German proposal and discussed this through their processes within the European Commission, and decided that they would introduce new hazard classes, both PBT VPVB and also PMT VPVM, into their regulation on classification, labeling, and packaging of substances. This should be this will likely be approved by the Parliament this Friday. There's been no objections from the European Parliament, so likely be approved, which means that in future in Europe, chemicals that are PMT or VPVM will have to have a warning label on them. So it'll be a hazard label similar to flammability or carcinogenicity or other things like this. So it will be a warning label so that if anybody buys this chemical or sells this chemical, they have to report this warning label. hopefully so that people will use the chemicals more responsibly and not emit them in water. I'll give you some background about how this was, the hazard criteria. And this is the typical scenario where you can think of how to define a PMT VPVM hazard. So this is your industrial zone. Maybe it's a chemical manufacturing plant, and it has some leakage into the groundwater. And some of the chemical will end up in, say, this fellow's well, and he's drinking the groundwater. This was a thing that was studied since the 80s, mainly in connection with pesticides on farms. But what they found was that how well a substance can leach in groundwater can be developed through this Gustafsson ubiquity score, or GUS. Gustafsson was the man who developed this. But it's a function of the half-life in the soil. So how long does it take for the substance to be degraded? That's the P. And the M is how low is absorption to soil organic carbon, and this can be measured in the lab. So the higher the soil half-life, the larger number of days it will not degrade, and the lower the M, the more likely it is to be in the groundwater. And so this is what he defined, Gustafsson, as this is the zone of chemicals that have this combination of P and M are groundwater leachers. These are non-leachers, and this is hard to say. So this was kind of the starting point to define the criteria. And so when you are assessing for PMT substances, you first look if your substance has an organic chemical. And if it does, then you should check, is that chemical persistent? What's the half-life? If if it's not persistent, but it has a low half-life, you can say it's a non-PMT substances because, for instance, it's readily biodegradable. It doesn't last for a long time in the soil. But if it does last for a long time in the soil, you assess for mobility. What is absorption? And can it be transported very fast? And if it can be a very persistent, very mobile substance. Or if it's just a little bit persistent or a little bit mobile, just enough to be called, that'll be a PM substances. And then you look for toxicity, and then you can see if it's also a PMT substance. So some substances are PMT, some substances are VPVM, some are both, and many substances are neither. A little bit more detail on how we look at persistency in Europe is we have defined criteria. This is based on a regulation called the REACH regulation, which says what the definition is. So for soil, if it has a degradation half-life of greater than 120 days, it's considered persistent. And if it's greater than 180 days, it's considered very persistent. And this is similar to freshwater sediments, such as below a lake, which is also relevant for PMT substances. And freshwater, there's freshwater half-lives too. So if it lasts longer than 40 days in water without degrading, it's considered persistent. We also include marine water and sediment in this definition, even though we're really concerned about freshwater. For mobility, the thresholds that they made after much discussion, and this took many years because this was a very new criteria, and it was like a lot of meetings and a lot of discussions at a very high level to come up with these log KLC thresholds, which is again defining mobility. It's a partitioning between soil organic carbon and water. If the log value is less than 3.0, it's considered mobile, and less than 2.0, it's considered very mobile. And this can be determined, basically, this is the definition. So I wrote a lot of text here, but you can read it at your own time, but it can be measured through organic carbon water partitioning in soil, sludge, or sediments. And it's mainly there to protect against subsurface or groundwater transport. Briefly on the discussion about where these thresholds came from, one of them was just looking at what are the log KLC values of chemicals that are in drinking water. So if you plot them all, you would have a histogram like this. And so it was a lot of definition. Where do we put in these thresholds? How many chemicals do we want to protect? And this was a distribution, and this was a big part of where this discussion went. And there's also other data that was used in addition to this empirical data. There was also that graph I showed you earlier called the Gustafson ubiquity score. There was also that these values were used by groundwater experts in Europe as working values to when they should look for chemicals that they should identify in groundwater. And there's some overlap with the biocide regulation in Europe, as well as the United Nations Food and Agricultural Organization guidelines for pesticides and leaching tests. And of course, industry also, or not industry, but the European Commission also had to measure the socio-economic impacts. What would be the effects on the water industry, on the chemicals industry, on other people from putting in these recommendations in place. So one thing that I hope will happen next is that now that these regulations happened in Europe, that maybe other regions of the world will start also adapting something similar to the PMT VPM criteria that we have in Europe. And in 2020, with Biaojin from Professor Biaojin from Guangzhou University and colleagues, we were looking at how this could be implemented in China, and we identified the Minister of the Environment in China, the regulations on chemical substance environmental risk assessment and control to control the emissions of hazardous substances. They do not, for substances that are not yet included in the inventory of existing chemical structures of China, they should be assessed for hazards. And we think this would be a good opportunity to assess new chemicals if they meet the PMT-VPM criteria to potentially lower emissions. And another area where the PMT-VPM criteria could be implemented is in the United Nations GHS, or this is the global hazards. And this would make it an international hazard class. It would make it a global criteria. And the EU is already planning on making an informal working group to bring this up as a new hazard criteria at the UN GHS level. So now, looking at the time, I'll go into how to detect these emerging PMT substances in case there are people interested in looking for them in their own local water. Now, one thing to consider is one of the reasons these substances were not seen much before was because they were very difficult to detect. And so we refer to this as minding the gap. There was an analytical gap. On the top was chemicals that you can analyze with the very common technique of gas chromatography. And this was chemicals you could measure with the also common technique of reverse phase liquid chromatography. And this is log DOW, which is not the same as KOC, but it's kind of related to mobility. It's an indirect indicator of soil mobility. But we can see there's a lot of space below the very low end of the log DOW scale where these chemicals cannot be measured using standard techniques. And we also looked at chemicals that are currently regulated, for instance, under the Stockholm POP regulation or priority substances in Europe, and they're all in this easy to measure domain using new techniques. But now there's been a lot more focus on how to measure these highly mobile chemicals. And some of these new techniques include hydrophilic interaction liquid chromatography, iron chromatography, capillary electrophoresis, and supercritical fluid chromatography, and also some novel enrichment techniques. And these are needed because when you're looking at these very mobile chemicals, they also sometimes have the same mobility as salts, like just simple sodium or potassium or calcium. And you have to get these salts out of the water when you are looking for these very highly mobile chemicals. And ever since we can do that, we can see a lot more things. So we took we combined the new PMT VPM criteria. We took an estimate of emissions in Europe, and we used these new techniques, and we were able to find a lot of chemicals in water that have never been analyzed before. And so in this next slide is some studies that I was involved in, and also other colleagues, of new substances we detected in drinking water and drinking water sources. And as you can see, they have quite unique structures. They have a lot of functional groups. They have sometimes very bizarre 3D structures. They're often charged. So these are sulfonic acids, so that they'll be negatively charged in the environment. But these are new substances that we're now able to detect in the environment, and many of them are PMT-VPM substances with this new methodology. We've also, again in collaboration with Yaojin from the Guangzhou Institute of Chemistry, CAS, we also did some screening studies of looking at existing monitoring data. In this case, what are the pharmaceuticals and personal care products, also called PCPs? Which one of these would meet the PMTV-PVM criteria, and what were their concentrations? And we could also identify many of these substances in Chinese drinking water and groundwater that could get more attention based on their persistence and mobility. And now I'll move to the final part of my talk, and that's about zero pollution and how can we get zero pollution of these substances. And I'm going to compare something called the toxic-free hierarchy versus Pandora's box. And I brought Pandora's box here because this is this old Greek myth that Pandora got a box with a lot of diseases and all the world's ills inside. And she was told not open it, but she did not know it was in the box, but she opened the box, and then everything became distributed in the environment and you could never get it back in again. So this is basically, how do we keep things in the box? And the toxic-free hierarchy, this was written by the European Union. This was a chemical strategy for sustainability. What is the best way to have, for instance, zero pollution? And the number one way they recommended was to have safe and sustainable chemicals, which in this case would be chemicals that are not persistent and mobile in commerce. The second one is if they are persistent and mobile, that you minimize their use and control their emissions. And the last is the most expensive last case resort, and that's to pay lots of money to eliminate them and remediate them from your drinking water. I will go through the different stages of this triangle, and I'm doing it based on this project that I am leading with Sarah Hale called 0PM, which is looking at these prevention strategies, prioritization strategies, and removal strategies. This is a very large European research project that will be running from 2021 to 2026, and we are trying to develop this for PMT-VPM substances. So one thing, starting from the bottom of the triangle, with removal, ideally what you want is for all chemicals in the environment to be removed with these types of techniques, which are the cheapest and very easily to be done. And sometimes they're even called natural techniques because we're just using natural processes. That's bank filtration, using river banks to filter water, aeration, bubbling air through the water to get the chemicals in the gas phase, or you can filter with sand or use some sedimentation. You still have to look out for PMTs in this process because sometimes you can put the PMTs into the atmosphere. And also with this, all your PMT VPMs will end up in the sludge. You can also use different advanced treatment techniques like foam fractionation, which I think has a lot of promise. That's when you make a kind of a soapy film on the top of the water and remove the foam. This has a lot of technique. You can use activated carbon and ion exchange, as I mentioned earlier, and nanofiltration. But all these techniques will give you the PMT, VPM chemicals in a concentrate or a sorbent, and then you have to deal with that. And as I said, like the price can range from 0 to €1 per cubic meter. And then there's also a lot of research that needs to be done of how can you remove these concentrated PMT, VPM chemicals or PFAS, and there's different technologies to do that too. You can use electricity or oxidation to try to destroy the molecular bonds, but then you have to watch out for byproduct formation and energy consumption. So this is something that needs to be researched. You can also use a lot of energy in the form of burning it or pyrolyzing it or milling it. But if you burn these enriched chemicals or activated carbons, You have to look at what are the volatile emissions. You have to be mindful of what energy is being produced. So you have to optimize that. And can this technology actually be upscaled to, say, a city level? And then there's landfilling. That's always a result. But then if you want to go in a landfill, these drinking water residues like concentrated sludges and brines, you're going to have to worry about your leachate emissions. So this is not recommended. Something to research. Minimizing and control. One of the techniques that we're looking at is to group these hazardous substances into one, like for instance, all the pesticides that make TFA, you group them into one, and then maybe you make a strategy to reduce their use or minimize their use so that they're making less TFA. And the similar with the refrigerants. And actually recently now in Europe, they said they are going to try to ban all precursors of TFA in Europe. So they're actually going ahead of the Montreal Protocol with this one. But this is a substance grouping based on a use. Other groupings that we're looking at are triazines. If we, for instance, all these triazines like melamine and cyanuric acid, they're all persistent and mobile in the environment. So maybe we want to make a group approach of regulation to get rid of or lower the use of all these high volume triazines. At the more local scale, it's just a strategy of source control. So that is when water companies see these chemicals in their water, the very first thing they should do, perhaps help with the state or the government or local authorities, is find out where are these chemicals coming from? And often the polluter might not even know that they are polluting. But then the next step is to get everybody to sit together to work to find a solution to lower emissions, because it's always cheaper to lower emissions, or mostly it's cheaper to lower emissions at the source of the emission rather than downstream at the drinking water facility, because then it's transported on the environment in the middle, and it's not as effective because of these diffuse distributions. And it's more economic for everybody if it's handled at the source. And also the person who's polluting can also contribute to the cost, which is called the polluter pays principle. They have an example of this in Sweden. They call it the REVAC approach. I just put that there in case you wanted to look it up. In the interest of time, I'm going to skip these next two slides, and I'm going to talk about prevention. This is about making safe and sustainable chemicals to replace. So one concept is the concept of green chemistry. Now, green chemistry has always been about making chemicals that were better for the environment, and they looked at, for instance, the carbon emissions of producing the chemicals. But the definition of green chemistry should be extended to also look at processes like biodegradability, and of course, if they're non-toxic. Ideally, we want all the chemicals that we're using to be at some point biodegradable and non-toxic, unless they have to be persistent for some reason. Another approach is called safe and sustainable by design. And that means when you're designing a material or a product or even a chemical, that you think about the whole life cycle and you think, how can I avoid using any PMT, VPVM chemicals in my product or in the life cycle? Unless, of course, it's obviously essential. And in some cases, it is essential, but it's a large discussion now. How do you define an essential chemical? For instance, with the refrigerants, you could argue that these trifluoroacetic acid precursors are not essential as refrigerants because there are replacements. You can use technology based on carbon dioxide or ammonia to replace those PFAS refrigerants, and so they're not essential. There is a replacement. Another way is to increase regulation. So we're putting the warning labels on PMT, VPM substances sold in Europe. This will also be a good indicator for those buyers of those chemicals that they should think about the risk that they could contaminate water if they're used in an inappropriate way. Now, if this was on the UNGHS level, then there'd be more regions than Europe that would have this hazard label. Something else that's related to what I said previously is called alternatives assessment. There's different tools that are out there to help industry choose what chemicals go in their products. And what they can do is they can look at the hazards of the different chemicals they're choosing. And examples of these were the CTSA or a green screen or the European Commission's DGE. These would help people choose what chemicals that were in their products, but none of them had mobility considered in them. And so we're saying in these tools that people are using to choose chemicals, also consider PMT, VPVM. There's also a lot of data gaps that need to be addressed. One of the biggest concern with doing this is that for most of the chemicals that are being made and are registered, there's very little persistency data. So there is a need to actually go out there and measure persistency, especially in the soil for more substances. And one of the ways we recommend doing this is to use benchmarking approaches. So for instance, you would have a water system or a soil system, and you include a chemical that you know its half-life and degradation, and then you compare the degradation of that substance with the other new substances you add in. This might be a cheaper, faster way than using the more common method following OECD 309, and that's to make a radio-labeled version of the chemical and then tracking how the degradation pathway of the radio-labeled substance. This is quite expensive. It takes a lot of time, and part of the reason why people aren't measuring persistence is because it's expensive and takes a lot of time. So we just need more persistency out there, and even if their methods are of not the same level of quality, there's a huge data gap to fill. We also should get more data on mobility. Now that they were using the log KOC data to measure mobility, there's a lot of substances out there where this is not known, partly because of this analytical gap I was talking about earlier. It's very hard to measure these in the environment and in soil because you have to separate them from the salts and everything else. But it'd be good to know what's the impact of soil properties like pH, ion exchange capacity, counter ion competition, the diversity of organic and mineral content, how soil processes affect absorption. And to try to understand how do these mobile substances are transported in the environment. And I'm often asked, what do you do when you have a chemical that has a large range of log KLC values? What do we do that for defining a PMT? We generally look at the smallest KOC value that's been measured in a soil. That's the conservative approach. And there's also a lot of data related to toxicity, because similar to how we don't have mobility data for a lot of the most mobile substances, we don't have a lot of toxicity data either, because these samples are really hard to analyze, say, in cell cultures. But you can use these new analytical methods to measure the toxicity better. And the two things that we're looking at in particular is the derived no effect level in the general population, especially through oral exposure or drinking water, and what is the predicted no effect concentration for aquatic organisms, because this is what a lot of fish will be swimming in. Something I say that some people, toxicologists don't like too much, but I'll say it anyway, is a very persistent, very mobile assessment and novel approach methodology, because you could argue that if all VPVM substances are hazardous, you don't have to measure their toxicity because exposure is going to be so high that we should just avoid them anyway and not measure their toxicity. And once these, another thing I think that should also be done is if these chemicals like TFA that are accumulating global, we should be more conservative about their toxicity. So we're saying that TFA is non-toxic, but we see that it's accumulating. But maybe we should assume it's more toxic than it is, just to make sure that there's no unexpected risk. And I also just want to mention, sometimes I get the response from the chemical industry that all this extra regulatory work and testing costs money. But This is a study of the economical impact of introducing European chemical regulations like REACH. And they found that since the introduction of these new stricter chemical regulations in Europe, the European chemical industry keeps expanding in profits each year. So there's not been any real indication that these new chemical regulations have disrupted profits. And we only see cost savings because we can show that these new regulations will save costs in health costs, they'll save costs in remediation costs. So usually these are good from a socioeconomic assessment, but this is an overall picture, but it's not always, there is sometimes a lot of cost saving in switching to safer chemicals. And things that we have to do going forward is understand the different perspectives and why they're wanting to use chemicals. Why do people want to use persistent mobile chemicals? What are the drivers in the economy? We have to understand this if we're going to phase these out, but also material scientists and designers should learn to design things without these chemicals. Maybe we're not thinking of this before. A lot of the people making products with PFAS never thought about their environmental consequences. So we have to get material science and designers in this as well. And then also develop green innovation so that businesses that want to make environmentally friendly products will start to think about switching to safer chemicals. So this is how we prevent. So this is my last slide, and this is how I'd like to conclude, that to get reduced zero pollution from persistent mobile toxic substances and very persistent, very mobile substances, all you need is love, of course, but you need new markets for the safer alternatives to PFAS and PMTs. We need to get this regulation from the CLP in Europe to maybe the Chinese regulations and the United Nations as a new hazard category or a strategy for lowering emissions. We need more science and transparency on PMT data. And then on minimizing control, we need to lower emissions by finding out who is emitting them and how to reduce those emissions, and especially in areas that are ecologically vulnerable, and particularly for substances like TFA that are accumulating in the entire planet. And finally, we also need to do research on innovative low-tech remediation ways of getting rid of these substances because they're going to be in the environment for a long time, regardless of regulations. And so we are still going to have to be cleaning them up for a long time. Okay, and with that, I would like to thank you very much for your attention. And I'm also giving my acknowledgements to my funders from the German Environmental Agency and the European Commission and my close collaborators, Sarah Hale, Michael Neumann, and Ivo Schliebner. Thank you very much.
Okay, thank you. Thanks, Professor Arp. Thanks for your interesting presentation about the PMTs in water. Hans-Peter just talked about the source of PMTs and the toxicity treatment assessment, the detection by the European. And he also talked about the zero pollution strategies. I think the PMTs in water is not just a simple question. It's really is an integrated issue. I mean, this problem includes the original production, the use, and the treatment, and the toxicity assessment, and the social acceptance of these concepts. So it's really many experts we should to research and studied. I think there must be some more questions about your presentation, which is really frontier aspects of PMTs. So let's move on to the communication. Again, I must to see any question, the audience, you could raise your hands or type your question in the chat box, then I can see. Because this is this presentation is the stream, is a live stream casting, so I can't see the comments from other platforms. I just can see the comments or questions in Zoom. So the volunteers need to copy the question or suggestions to the chat box. And I must encourage the young students or early career scientists to ask questions and communicate with the world famous scholars. It's really good opportunity to express your scientific thoughts. Okay, anyone have any question? You can raise up, hands up. So firstly, I may ask a small question about firstly about the toxicity of the PMTs you mentioned. Are there any reports about their accumulation in human body? I mean, if we drink the tap water every day, they contain the PMTs even in so much low concentration. Part per billion, I think, very low than part per billion. So what's the main risks? Will they easily be absorbed by our body, or the PMTs will excreted out by ourselves?
Yeah, I would say in most cases not. Most of them. There might be some exceptions that have a particular binding to a receptor, a protein receptor, and this might be the case definitely for some of the substances that are borderline mobile. Like for instance, PFOA is a PMT substances that can accumulate. It can attach to certain proteins, but the majority of them, no, they will be rapidly excreted. However, the thing is, the exposure is what they call in the exposome in the drinking water. So even if they're rapidly excreted, we still reach equilibrium based on the drinking water. So they don't accumulate over time. They depend on what we're drinking every day. So it's more of an equilibrium situation rather than an accumulation situation.
Okay, yeah, I see there's two audience have raised their hand up. So will the volunteers open the audience mic? Then they can ask a question directly. Does Dr. Min Xu there? Maybe the chair is not there. So I think the PMT in water is quite low concentration. So what's the extraction, the extraction method for determine the PMTs in water? I think the extraction is really very important for this so low concentration contaminants. What's the extraction method?
Yeah, well, there's different extraction methods, and maybe I would have to refer to the references there. But I mean, generally, you're doing solid phase extractions first, and then it's about once you're extracting the solid phase, it's finding a polar solvent to maybe separate things like ethylene glycol, and then you have to find out ways of repressing the signals of co-eluting salts in your method. But it's a huge research area, and people who are doing the analytics are actually, I think, spending more time on what you said, extraction method, than they are, or the enrichment method, than they are on the analysis methods.
Okay. I just reviewed the paper you published, and I found that you use the multi-layer solid phase extraction to. We also invented some solid phase micro extraction to extract the contaminants from water. We use the porous carbon to coat on the fibers rather than the PDMS, the commercial PDMS in the fibers. Its extraction efficiency is really very high than the commercial PDMS. Maybe the solid phase micro extraction will be another choice to extract the contaminants from water.
Yeah, no, that's interesting, and I do have colleagues working on that. I never heard of your technique, but it looks good. But I know many are trying to develop passive sampling techniques like POCUS or ChemCatcher or DGT to also measure these. But yours sounds very intriguing. I don't know. Oh, I have.
Okay, yes, there is a question. Dear Professor and Teacher Arp, from the environmental risk, PMT substance will replace PBT substance as the main research direction? Thanks.
No, I don't. Thank you for the question. I don't think it will replace it. I think it'll be a general focus on persistent substances in general, because to me this is the common thing. And with PBT, PMT, and also microplastics, these persistent chemicals that accumulate in the environment. And when we talk about PBT or PMT, we're only changing the exposure route. So some chemicals will accumulate in the soil, some will accumulate in the water, some will accumulate in the lipids. So it's really, the focus should be, I think, on all persistent chemicals, but we can separate their exposure pathways. Thank you for the question.
Yeah, thank you. I
see some hands.
wonder, yes, the audience mic will be open or not? So maybe Yaoshi from institute or from our institute, you can text your question in the chat box. Yeah, there is another question. Is PMT difficult to detect, or is there a standard method for detecting all PMT? If I want to study the distribution of PMT in my city, what advice and experience do you have? I could copy this question to the chat box.
Yeah, no, I would say there is no one size fits all method, unfortunately. But I do see a lot of potential in supercritical fluid chromatography that can measure quite a lot of them. And also, and some people are developing helic methods, but they're not so good. But I could refer you to some citations by Daniel Zahn and Torsten Riemsma. They are analysts that are making a lot of new methods, but there's not one size fits all.
Okay, then I can see the audience. So, Ms. Yosh, you can ask question. Open your mic. Yeah, you can ask your question. Yeah.
Hello.
Oh, this is Chunhu. Yeah.
Dear Professor Up, thanks for your presentation on the PMT substance. I'm Hu Cheng, come from Nanjing Forestry University, and do some work on enriching organic pollutants by solid phase micro extraction. As you said, PMT should gain as much attention as possible. Actually, some of PMT is in environment. I belong to trace level. So we need drink, but as we all know, it's difficult to find the water resource with zero pollution. Will this trace PMT do toxic effects over a limited lifespan of humans, such as 80 years? Also, is there a safety concentration standard in future?
Well, I would say that the goal is to make sure that it does not have any effect on human lifespan. That is the goal. Right now, I think there is already evidence that the PFAS contamination would affect, the concentration is so high, it would affect some of the population. And I think maybe in some local areas, they'll have additional contaminants as well. And we've seen, as I mentioned briefly, levels of 1,4-dioxane and possibly melamine being a concern. So I think the PFAS concentrations we're looking at too late, and for other PMT substances, it's getting worse. So what we're trying to do is now, I think, prevent it from getting worse. But I do think at the population level there might be some effect, but it's too much of a broad range of chemicals to say exactly where this is.
Okay, thank you for your answer.
Thank you for your
And
question.
in my university, remediation method such as wetland, near nature method to repair or to decontaminate the PMT.
No,
Maybe
yeah,
a good method.
No, I think so. I'm very much in favor of nature-based solutions. I feel, for many reasons, I feel like the pollution that we make should be able to be cleaned up by nature-based solutions, because that's obviously the best for climate, and it's also ultimately cheaper for urban environments, for people, for cities, than paying for extremely high-tech water treatment. So I feel like our use of chemicals and emissions of chemicals should meet what nature-based solutions can take care of. Yeah.
Okay, thanks.
Okay, the next question, I think, Yoshi, you can ask your question now. I just
can you
hear
hear my
voice.
voice?
Yes, yes, you can open
Hi,
your camera.
Hi, Professor Hans-Peter. I'm Yoshi, a student from Institute of Soil Science, Chinese Academical Science. Your presentation is very interesting and impressive. As you mentioned, there are still some limitations to the analysis of PMT substance in water. The soil environment is more complex than the water environment. So the determination and analysis of PMT may be more difficult. So to explore the environmental behavior of those substances in the soil from which several aspects. That are my questions. Thank you.
Yeah. So yeah, but it is a big topic, and it's a large list of substances. But what I can say is that the best way to approach this is what we've done recently was when we made a list of PMT VPF substances, and I've published on this recently, and I can give some more citations for this. But we also look at which of the substances we can analyze and which of them we can't yet using known methodologies. And this is something, an immediate thing to look at, also in combination with which ones have not been actually looked for yet. And this is sometimes how we find new chemicals. And when we are looking at it systematically, starting from the chemical to what analytical techniques will recognize, oh, these ones, we don't know any technique to measure them. Maybe we should develop a technique to measure them. Or you might look at the other end, it's like these, and they never been monitored yet. And maybe we have a reason to monitor them because they're being produced at a large quantity. So again, because I'm referring to a whole group of diverse chemicals, you almost have to look one at a time and at the list and think, what can I measure? What do I want to learn how to measure? And then you can come up actually with some new science going forward to deal with this. But I feel like I should give some citations to present clear what I'm talking about.
Thank you.
Okay.
Thank you for the question.
There's another question from Hui Cao. Dear Professor Hans-Peter, I would like to ask whether there is any difference in the treatment of PMT and VPVM substance. PMT substance seem to have a probability of degrading through relevant treatments, while VPVM substances seem to never disappear.
Yeah, yeah, that is a good point. And also for clarity, some substances can be both PMT and VPVM, and these are the words. Sometimes these are called VPVMT. But I can just mention that is that PMT, they have a lower threshold for mobility and persistence because we know that they're already toxic. And so we know we have to do something about them because their toxicity has been demonstrated. VPVM, they're in the environment for a longer time and can accumulate for a long time. And therefore, they are at risk even if we don't know if they're toxic or not. And I say if we don't know if they're toxic, because many cases we assume they're not toxic, and then later came this new research to show that they were toxic. So that is why I'm particularly worried about the VPVM. They have a higher chance of accumulating in the global environment and a greater chance of being irreversible in the environment. So yes, I am very worried about those, even if they're not toxic. Thank you.
Okay. Okay, then another question. From Li Ying Song. Through your report, we have a deeper understanding of water pollution. Water is very important to us. I have a question. In preventing pollution, most use non-toxic and green products. This application in practice is feasible. I mean, she may ask we should use more non-toxic and green products without the using of any toxic substance.
Yeah, absolutely, and that's what we should all be striving to go towards. And I mean, and also how to do that is.
他没有让我说话。
Sorry.
Okay, you can go on.
Yeah. Okay. Yeah. Sorry. Yeah. So in many cases, that's what we should do. And just to give some certain examples, like some dish detergents, they might have some ingredients like benzotriazole that we consider persistent and mobile toxic, but you can come up with a dish detergent that maybe is good and also as good as protecting the metal in the machine without being PMT. So the idea is to switch to green solvents. But the key thing to mention here is that often when we're saying green substitutes or it's not a scientific definition. It's usually a marketing definition. And so sometimes companies will sell something as a green alternative, but not test if it's green or not. So sometimes they say we need more legal definitions of what do you mean by green, or is it a green substitute, so that we can have a scientific based definition of a green and not a marketing definition of a green substance. And so I am also I would also encourage that as well. That's why when we say green chemistry, we should consider biodegradability and low toxicity as the good chemicals to use, and we know they exist.
Okay. Oh, sorry for Hui Hui. So I didn't mention that your mic is also opened. I just read your question. So do you have any other question want to ask directly, Hui Hui Cao?
Oh yes. Can you hear me?
Yes.
Okay. Hello, Professor Hans-Peter. I'm Cao Huihui. I come from Institute of Sciences in Nanjing. I have another small question to ask you. Is the toxicity assessment of PMT or VPVM substances mainly environmental toxicity or human health toxicity?
Yeah. Well, the answer is we don't have much data on a lot of these substances in terms of both, human health and environment toxicity. But we need both, so we need more research there. So one of the things that we're doing in 0PM is doing a lot more human health studies on PMT studies, but on VPVM and PMT substances. But I also think we should look especially at aquatic ecotoxicity mostly, because these can increase in lakes and in rivers as well. So these are my two biggest priorities: is humans and lake systems or freshwater systems.
Okay, thank you.
Okay, anyone have any questions? Talking about the treatment of the PMTs, in your slide, you just mentioned the main strategy for treat PMTs in Europe is the oxidation and the absorption by activated carbon, I think. So I just wonder, do you think a strong solvent will solve the problem? We also working with new solvents such as porous carbon just mentioned earlier, and which is produced by the crop residue, the microalgae, and by pyrolysis, and we activated them by the solvents, and its sorption capacity is really very high, stronger than activated carbon, I think. So maybe this is a potential resolution method, but what is the post-treat of the sorption method? I mean, how to treat the solved, yes, post-treatment.
Yeah, no, yeah, this is the thing, and I say, and just in general on treatments, yeah, I think there's a lot of technology that can be developed, and there's a lot of promising technology that can be developed, and it should be developed. And I'll just say two things. One is yeah, about your technology, it sounds good, and I mean, of course, you have to upscale it, but yeah, you might always have the solution of what you do with the contaminant that's on your sorbent. What do you do then? And there, it's really the best thing to do would to be either destroy it through something like electricity or with heat. And if you do that, you have to really control emissions from that process, because this is something that I've seen in all the technologies that do that, like, such as electrochemical oxidation. Maybe they can destroy 99 or 98% of the chemical, but there might always be 1 or 2% of something that will go in the air or the water. It's the same with incineration. If you do something very simple, like put it in a municipal waste incinerator at 1,500 degrees, you still might get something coming out the chimney. So that's the thing to watch out for. And to always check. So, but I'll add also, in addition, regardless of the cleanup technology, and I do believe we can develop better cleanup technologies, it'll always be cheaper for society to prevent them than to clean them up.
Okay. I think maybe the audience have no question yet. So I have the last question. I have so many questions. So the last I ask a question regardless of the PMTs. Since many of the audience today are young students, the PhD candidates, master candidates, or the early career scholars. So we will give us some suggestion about how to do good research, just like you have so much great achievement. Give some comments or suggestions to the young scholars.
Well, I can only say is number one, always be curious. That is the rule number one. And then rule number two, I would say, is to find a path that you find that you can give a meaningful contribution to, so that you feel that based on your own interests. I can just give you my example. I was always very interested in the physical chemical properties of chemicals. So it's just interested in questions like, why is this chemical more soluble than that chemical? It was just a simple question, but I just found this just interesting to think about. But then the more I thought about it, then I saw more ways that this could be used to answer scientific questions based on my curiosity about what makes chemicals more soluble. So it can go into understanding sorption processes, transport processes. Why do some chemicals stick to plastics and some others don't? And then I found myself able to answer more technical questions. And then the more I could answer technical questions, the more people would ask me for advice, and then I would end up getting asked more interesting technical questions and interesting research. And so I think it was just that simple curiosity that got me onto the PMT concept and related topics, like my collaboration with Professor Yang Zhang, where we're looking at absorption to plastics and soil. It's all related to this basic fundamental curiosity.
Okay. So nice suggestion. And I think there may be some no question not. So thanks, Professor, for this wonderful academic communication. I think most of the audience have received more information about the PMTs, especially in water environment. I also learned a lot. And I may also sincerely invite you to write a review article for EEH if you are interested in. Maybe next time we can communicate with microplastics, what we also focused on. So thank you very much. Thank you. I may call it a day now. So see you.
Okay, thank you, and xie. Thank you for the nice time at this webinar.
Thank you. I can't see noisy.
Oh, I'll teach you next time. See you. Bye bye.
Okay. I can learn. Next time I can learn noisy. How to say
Yes.
bye bye.
Ha det bra.
Ha det bra.
Bye bye.
Bye. Thank you very much.